NEC 2005 Ampacity tables for underground ducts are generally applicable only for cables that are identical in size and all other characteristics. This means that the cables must have the same conductor material, insulation type, concentricity, rated voltage, and construction. B. 310.11 of the NEC allows for the adjustment of ampacities for cables in a raceway based on low diversity factors. However, this adjustment only applies to cables that are identical in all respects, except for size. If the cables in a duct are of different sizes, the ampacities for each cable size must be calculated separately. The following methods can be used: firstly, direct calculation; secondly, adjustment factors; and thirdly, computer software. Let's discuss each of these methods in detail. Firstly, direct calculation involves using the ampacity tables in NEC 2005 for each cable size and adjusting for any applicable conditions such as ambient temperature and grouping. These tables provide ampacity values for various conductor sizes and insulation types under specific conditions. To perform a direct calculation, begin by identifying the appropriate ampacity table in NEC 2005 for the cable's insulation type and installation method, which in this case is underground ducts. Locate the cable size in American wire gauge or KC mil and find the corresponding ampacity value. Adjust the ampacity value for ambient temperature if the actual ambient temperature differs from the table's reference temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. Use the appropriate correction factors found in NEC tables. Then, adjust the ampacity value for grouping if multiple cables are installed in close proximity, which can increase the overall temperature. Use the ampacity adjustment factors specified in NEC table 310.15. If other directing factors apply, such as voltage drop or harmonic distortion, apply these as well to determine the final allowable ampacity for each cable size. For example, consider 3 different cable sizes in an underground duct: 1/0 American wire gauge, 2/0 American wire gauge, and 3/0 American wire gauge, all with THHN insulation. First, find the base ampacity for each cable size from NEC table 310.16 before adjustment. Let's assume we are using the 75 degrees Celsius column. The 1/0 American wire gauge cable has a base ampacity of 150 amps. The 2/0 American wire gauge cable has a base ampacity of 175 amps. The 3/0 American wire gauge cable has a base ampacity of 200 amps. Next, adjust for ambient temperature. If the ambient temperature is 40 degrees Celsius and the table's reference temperature is 30 degrees Celsius, you might need to apply a correction factor from NEC table 310.15. For THHN, a typical correction factor might be 0.91. So, the adjusted ampacities are 1/0 American wire gauge 150 amps times 0.91 equals 136.5 amps, 2/0 American wire gauge 175 amps times 0.91 equals 159.25 amps, and 3/0 American wire gauge 200 amps times 0.91 equals 182 amps. Now, adjust for the number of conductors in the raceway. If there are 4 current carrying conductors, the adjustment factor might be 0.8. The final ampacities are 1/0 American wire gauge 136.5 amps times 0.8 equals 109.2 amps, 2/0 American wire gauge 159.25 amps times 0.8 equals 127.4 amps, and 3/0 American wire gauge 182 amps times 0.8 equals 145.6 amps. This method ensures each cable's ampacity is calculated based on its size and specific installation conditions. Now let's explore the second method using adjustment factors. An adjustment factor from table B 310.11 to adjust the ampacity of the larger cables based on the ampacity of the smallest cable. However, this method is only applicable if all cables are of the same insulation type and concentricity. Table B 310.11 provides adjustment factors for various low diversity scenarios. It's generally used when cables are of the same type but may carry different loads, and you want to optimize the overall ampacity rating. Firstly, determine the ampacity of the smallest cable in the raceway using the appropriate NEC table and any necessary directing factors for ambient temperature or the number of conductors. Secondly, identify the diversity factor based on the expected load characteristics of the cables. This factor is typically provided in Table B 310.11 and reflects the likelihood that not all cables will be fully loaded simultaneously. Thirdly, apply the diversity factor to the ampacity of the smallest cable. This adjusted ampacity can then be used as a reference point for determining the allowable ampacity of the larger cables, considering they won't all be fully loaded at the same time. For example, let's assume you have 3 cables in a raceway: 4 American wire gauge, 2 American wire gauge, and 1/0 American wire gauge, all with THHN insulation. The 4 American wire gauge cable is the smallest and is rated at 85 amps after adjusting for ambient temperature and number of conductors. If Table B 310.11 indicates a diversity factor of 0.7 for the given load conditions, the adjusted ampacity becomes 85 amps times 0.7 equals 59.5 amps. Now you can use this adjusted value to assess the adequacy of the larger cables, assuming they won't all be fully loaded simultaneously. This approach allows you to optimize cable sizing based on load diversity. It is important to note that the NEC provides specific conditions under which these adjustment factors can be applied, so always refer to the code for detailed guidance. Lastly, let's talk about computer software. Computer software programs often incorporate complex algorithms that take into account various factors such as cable size, insulation type, installation conditions, ambient temperature, grouping of conductors, and load diversity. These programs can accurately calculate the ampacity of each cable in the raceway while considering their interactions. These programs typically use iterative methods to solve heat transfer equations, ensuring that the temperature rise within the raceway stays within the allowable limit specified by the NEC. They can handle complex scenarios where multiple cable sizes are present and where the load on each cable varies. These programs often generate detailed reports that show the ampacity of each cable, the temperature rise within the raceway, and any limiting factors. This documentation can be valuable for ensuring compliance with the NEC and for justifying design decisions to clients or inspectors. For instance, you might input details about your cable configuration into a software program such as ETAP or SKM Power Tools. The software would then calculate the ampacity for each cable size based on the specified conditions. These software programs can also model the thermal behavior of the raceway to ensure that the temperature limits of the cables are not exceeded. This approach ensures a more accurate and comprehensive assessment of cable ampacity in complex installations. In summary, it is not always appropriate to use NEC 2005 ampacity tables for underground ducts when the cables have different sizes. The ampacities for each cable size should be calculated separately using the methods described above to ensure safety and compliance with electrical codes. Understanding these methods and applying them correctly is crucial for electrical engineers and installers to ensure the safe and efficient operation of electrical systems.